Hello, welcome everybody to Café Scientifique. And my name is Tobias Junginger. I'm from the Faculty of Science and Physics Department. Hey! All right, I'm a fan. That's excellent. Yeah, okay. I remember I gave a talk here before. But okay, no, today I'm only introducing the speaker. And it's really an honor to introduce today's speaker. We actually have a best-selling author today. And she's the author of the book Snorkeling Around Vancouver Island. But okay, today she will not be trying to convince you to jump into the Pacific Ocean in January, which apparently not such a bad idea. No, she was talking about, she also has a day job, so she is a professor of astronomy in the Physics and Astronomy department. Yay. Very okay. Very exciting. All right. So, and she's actually doing very well in her day job, as I can see here from the her CV. So, she got a PhD in 2000 from the University of Cambridge, and then she went to the European Southern Observatory, which is in Chile. Okay. And after that, she came to Victoria to take on CRC, it's the Canadian Research Chair position, very prestigious position. And since 2014, she is full professor at the university. And she had many awards and also many important positions. So I'm not going to list them all, but I guess one stood out for me. She was the president of CASA, which is a Canadian Astronomical Society. So Sara, please come up on stage and take it from me.
Great. Thank you, Toby, for the very kind introduction. It always seems strange to consider that I have a day job when I'm an astronomer. It feels like I should have a night job rather than a day job. Yeah, exactly. Well, the snorkeling is maybe my day job. So as Toby told you, I am an astronomer at the University of Victoria, and my field of research is studying the formation of galaxies and how galaxies evolve over time. So despite the fact that we think of astronomy as a very, very old science, so we've been looking at the night sky for literally thousands of years as a species, wondering about its origins, our origins. The study of galaxies is actually maybe surprisingly new. If I had been standing here 100 years ago, I could not have been speaking about the evolution of galaxies. And in fact, this year, 2024, marks a remarkable, in my opinion, anniversary, a remarkable centennial birthday of when, as astronomers, we really understood for the first time that the Milky Way is not the only galaxy in the universe. So I feel that this is a very timely evening to give a presentation, because really 100 years and a month ago was when we made this realization. And so given that, I thought I would start my talk with a little bit of a history lesson to take you from those moments when we realize that we live in this universe full of galaxies, before I tell you a bit about my own research. So our story of the history of galaxies actually starts way, way back in the 1700s. So in the 1700s, the astronomy of the day was the study of comets. People in Europe in particular were just nuts about the study of comets. And in particular, there was an incredible cachet associated with being able to discover a comet for yourself, because then you got to name it either after yourself or after your patron, for example. And so at the time, in the 1760s, there was a French comet hunter called Charles Messier. And he just lived for finding comets. So how do you find a comet? Well, when we look up in the night sky, at least with our naked eyes, the vast majority of what we see are stars in our own Milky Way galaxy. And stars are characterized as point sources and in patterns that don't really change very much. So although the stars move across the night sky, so they make a complete circuit of the night sky in 24 hours as the Earth is spinning on its own axis, the patterns, the constellations, they don't change. So the stars don't move relative to one another. So to find a comet, which is really just a big snowball in space, that whizzes into the inner part of the solar system and then slowly starts to evaporate. In order to find one of these things, the comet hunters were looking for two characteristics. First, they were looking for something that seemed to move relative to the other stars, night on night. And second, they were looking for something that wasn't a point source, because they knew that comets had these fuzzy, extended shapes and often had a long tail. So the way that you find a comet is you go out night after night, you look for some fuzzy object that seems to move relative to the background stars. So this was what Charles Messier was doing back in the middle of the 18th century. But much to his frustration, there were many objects in the night sky that looked fuzzy, but that weren't moving. So they kind of caught his eye because they were fuzzy, But then when he came back and he looked night after night, they were in the same place. So to avoid this distraction of fuzzy things that weren't comets, he made himself a list of these objects. And on his list, he had about 100 of these fuzzy but not comet objects. And this eventually became known as the Messier catalogue. So there are, as I said, about 100 objects in the Messier catalogue. And when we look at them with modern day telescopes, we can see that this collection of fuzzy objects actually has a very diverse set of origins. Some of them are the remnants of exploded massive stars, so-called supernova remnants, where we can see the shredded exterior layers of the star. So that's why they look extended and fuzzy. Others are the birthplaces of young stars. So we see clusters of young stars in clouds of gas and dust that are their birth sites. But others of these fuzzy objects are now what we know to be galaxies. But at the time, we had no way of understanding physically what they were. So this Messier catalogue was the first compilation of extragalactic objects, even though Charles Messier had no idea what he was looking at. All right, now we're going to fast forward to the early part of the 20th century. Astronomers are now starting to take pictures with telescopes of the objects in the Messier catalogue. And they start to realize the nature of some of these objects, so they can understand supernova remnants, they can understand the birth of young stars. But then they see that some of these objects have this strange spiral shape to them that they don't really understand. And they call these the spiral nebulae. So in astronomy, we use the word nebula to mean anything that is cloud-like. So if it's a cloud of gas and dust, we call it a nebula. But also if it was an extended spiral-shaped object, that also got called a nebula. And so astronomers were hotly debating the nature of these spiral nebulae. And it became such a feverish point of debate that in the 1920s, astronomers decided they needed to sort this out once and for all. And so they organized a debate between two leading figures at the time. So this was the so-called Great Debate. It happened in DC in 1920 between two astronomers based in the US, Harlow Shapley and Heber Curtis. And on the one side, Heber Curtis argued that these spiral nebulae were actually objects just like our Milky Way galaxy, but at great, great distances, so they looked very faint. On the other hand, Harlow Shapley said, this is ridiculous. In order to be so faint and so small, these objects would have to be at incredibly large distances that were just inconceivable. And instead, he argued that these spiral nebulae were just swirling clouds of gas and stars inside our own galaxy. So at this debate, the two astronomers put forward their arguments, but at the end, it was inconclusive. Neither could really convince the esteemed audience one way or the other. And so the jury was still out. Really, what we needed to be able to do was measure the distances to these spiral nebulae. So in order to do that, astronomers had to develop a way to measure the distances to objects, both within the Milky Way and potentially beyond. So now we're actually going to wind the clock back a few years, back to about 1910. One of the great centers for astronomy at this time was at the Harvard Observatory on the east coast of the US. This was where young men, because it was young men, went to forge their careers as great astrophysicists. And the director of the observatory at the time was called Edward Pickering. And he was mentor to all of these young gentlemen astronomers. But so the story goes, one day he got somewhat frustrated with his team and made the offhand comment, oh, for goodness sake, my housemaid could do better than this. And in my mind, I like to picture this light bulb going off in his mind as he realizes, oh, but wait, women could do this too. And sure enough, he did go ahead and hire his housekeeper to be part of his team. And this was the start of a revolution in astronomy. Sometimes Edward Pickering is cast as a somewhat sexist character who chose to hire women because he could pay them really less than minimum wage. But actually, in truth, he was a great supporter of women in science. And over the years, he recruited many tens of women to work under his direction at the Harvard Observatory. And it was their task to work through the mountains of data that the observatory was gathering. And some of the women in his team went on to make incredible discoveries. So, for example, the system that we use for classifying stars, even today, that was set up by Annie Jump Cannon, who was one of his first so-called computers. Another incredible discovery by one of his women, Cecilia Payne-Koposchkin, was to understand how we can measure the chemistry of stars just by looking at the light that comes from them. So this was incredible work that they were doing. But for our story, we care about a character called Henrietta Swan-Leavitt. And what Swan-Leavitt discovered was that when you look at a certain special type of variable star, so a variable star is a star that changes its brightness periodically over time. And she discovered that there was a special type of variable star such that its peak brightness had a tight correlation with the time over which it varied. Now, this might not sound particularly important, but what it allows us to do is to measure the distances to these stars very accurately. Because if we can measure the time of the variations, which we can do independently of how far away the star is, and if we know then how bright that star should be, we can compare it to how bright we measure it to be, and that difference in brightness tells us the distance. So this was absolute gold for being able to figure out the distances to stars. So in the early 1920s, another very well-known now American astronomer, Edwin Hubble, used this technique to measure the distance to one of these so-called spiral nebulae. He found one of these variable stars in a nearby spiral called the Andromeda Galaxy. And so in the early months of 1924, he announced to the world the distance that he had measured to the Andromeda Galaxy, which very, very clearly put it outside the realms of the Milky Way. So this was really the moment that changed everything for extragalactic astronomy, when we realized that these spiral nebulae were other galaxies much like our own, but at great distances. So that was the state of extragalactic research at the beginning of the 20th century. Now I want to take us to the close of the 20th century, just to see how far we had come. So the first sort of discovery that I'd like to point out has a nice connection with this historical story that I've just told you in terms of the name Hubble. So Hubble was the man who made these measurements to the so-called spiral nebulae. And he, of course, is also the namesake for the Hubble Space Telescope. So the Hubble Space Telescope, if you can believe it, the Hubble Space Telescope was launched in 1990. It feels like it's been with us for forever. So in a mere 66 years, we went from not knowing that there were other galaxies to launching the Hubble Space Telescope. I mean, if you pause and think about that for a minute, that means that somebody in the 1920s could have been at elementary school and been told, our Milky Way is all there is. And then in 1990, telling their grandchildren, we live in this universe full of galaxies. Because one of the very first things that Hubble did was take the space telescope, not the person, was to take a very, very deep picture of the night sky. So over the course of several hundred orbits around the Earth, the Hubble Space Telescope just stared at one patch of sky to produce an image called the Hubble Deep Field. If you take a look at this picture of the Hubble Deep Field, you'll see it is full of galaxies. There are 10,000 galaxies in the image that the Hubble Space Telescope took in those early years. And yet, that image on the night sky covers an area half the size of a grain of rice held at arm's length. So if you extrapolate those 10,000 galaxies all over the sky, we live in this universe full of galaxies. And so in just 66 years, we went so far in our appreciation. That image and other images that astronomers have been taking with modern telescopes show that we don't just live in a universe full of galaxies, but these galaxies are extremely diverse. They come in lots of different shapes and sizes and colors. And so another great advance that we've had in our understanding in this last century has been how we get this diversity of galaxies. And a big component of this has actually come on the theoretical side. So now with modern computers, we can build entire universes inside a supercomputer. We can set up the initial conditions of the universe. It sounds so arrogant that we can do this, but we can. We can set up the initial conditions of the universe. So we can put in all of the physics laws that we know, all of the material that we know is out there in the universe, and press go and let it run. Let it run not for the 14 billion years that is the real age of the universe, but obviously at a greatly accelerated rate. And we can see galaxies forming. And so we've been able to simulate the growth of structure that we see in galaxies. And we've learned that the massive galaxies that we see around us today, like our own Milky Way, are formed in what we call a hierarchical sense. So that means you start off with lots of little galaxies and they merge together and form bigger ones over time. And this theme of galaxy mergers is one I'll come back to later in the talk. Okay, what else did we learn about galaxies in the last 100 years? So at the close of the 20th century, another really important thing we had learned is that at the center of essentially every galaxy, there is a supermassive black hole. Black holes sound as if they should be science fiction, but they are very much a reality. Sometimes they're just the mass of one star or so, but sometimes they come in this supermassive variety. So for example, at the center of the Milky Way, there is a black hole whose mass is 4 million times the mass of the sun. And so we'd figured this out by the end of the 20th century. We'd not only figured out that there was a black hole there, but we'd measured its mass. And we'd done that by watching how stars in the center of the galaxy were orbiting around this invisible mass in the middle. And this is physics that had been worked out in the 1600s, watching how objects move around other objects and what that means for the mass that they're orbiting around. Simple physics. We teach this to our first-year undergrads. But it allowed us to figure out that galaxies have these supermassive objects lurking in their center. The very same physics of watching how things orbit and what that tells us about the mass in the middle revealed another rather disturbing truth to astronomers in the 20th century. And that is that 90% of matter in any given galaxy is not normal atoms. It's not protons, electrons, the kind of atomic and molecular material that we're familiar with. It is this so-called mysterious dark matter that we still have no idea what it is. But again, we were able to figure out that it was there just by watching the orbits of stuff. So we'd done a lot of cool things by the end of the 20th century. And this is the moment at which my personal story begins, because the end of the 20th century was when I started my own research career. So I started my PhD, I'm going to terribly age myself now, in 1997. As Toby said in his introduction, I was doing my PhD in Cambridge, as you can probably tell by my accent. I'm originally from the UK. So I arrived in Cambridge, a fresh-faced graduate student in 1997, excited to start my own personal journey of research against this backdrop of all of these exciting discoveries. I didn't really know what I wanted to do. I was pretty sure I wanted to work on galaxies, and I was also pretty sure that I wanted to work on observations rather than on theory. But apart from that, I wasn't really sure. So luckily for me at Cambridge, the way that the graduate program worked was all of the new graduate students got to go visit with the different professors and chat with them about the kind of research they did. And then you got to choose who you ended up working with. And I remember going into the office of my eventual supervisor and him telling me that he worked on a topic called quasar absorption lines. I had no idea what this meant. I barely even understood what the individual words meant, let alone how it all combined together to make a field of study. But after 2 hours of chatting with him in his office, I was hooked. So let me just tell you very, very briefly how this quasar absorption line thing works. So what is a quasar? Well, a quasar is basically one of these supermassive black holes, but it's doing something very special. It's busy accreting material that happens to fall within its gravitational realm. And so it's accreting all of this material, and it's like material going down a plug hole. It's sort of swirling down towards this central position. And that creates a lot of energy, and it makes the object glow very brightly. So essentially, a quasar is just a very massive black hole that's in this feeding state that makes it very, very bright. Now, as it happens, for this particular research, I don't actually care what a quasar is. All I care about is that it's very bright. Now, because quasars are very, very bright, it means you can see them even when they're very far away. And indeed, at the time when I was starting my PhD, quasars were the most distant objects that you could observe in the universe. You could observe them so far back in time that the universe was only a mere 2 billion years old. So the universe is now 14 billion years old. So we could see these quasars even when the universe was quite young. But what made this field special was that we could study the light coming from these very, very distant, very, very bright objects. And as the light was traveling through these billions of years of space, it was traveling sometimes through galaxies that just happened to be in between us and the quasar. Galaxies that would be way too faint to study directly from their starlight. But because they happen to be aligned with this background quasar, they used up some of the light coming from the background quasar. And we could take a spectrum of the light coming from this background quasar, and we could actually figure out a lot of information about this intervening galaxy. And in particular, we could figure out the chemistry of this galaxy. Now, there are some chemists in the audience. Their ears pricking up, I know. So we could actually measure the chemical abundances, how much silicon, how much sulfur, how much magnesium, how much zinc is in these very young galaxies. And this was important because it meant that we could figure out what kinds of stars had already formed in these galaxies, because different types of stars produce different chemical elements. So this was what I spent 3 years of my PhD doing. Another very important thing that happened during my PhD, and some of you I know are long-term disciples of Café Scientifique, and so you will know the previous host, John Willis. So John was also a young graduate student in Cambridge, 2 years ahead of me, and we are now married. So that was the other important life thing that happened in Cambridge. John was 2 years ahead of me. He was very thoughtfully extremely slow finishing his PhD. So he actually graduated at more or less the same time. So we both got our PhDs in 2000, and then we needed to find jobs. At that time, it was a very exciting time for observational astronomers because there was a slew of new optical telescopes being built that were the biggest, the most powerful at the time. A couple of them were being built on Mauna Kea in Hawaii, but several were being built in Chile because Chile has very high mountains. So in the northern Atacama Desert, you have all these extinct volcanoes. They're very remote, so you're far away from light pollution. And you're also very high, so you're above the low cloud layer, and it's also very dry. So John and I wanted to continue our research in astronomy. We also wanted a bit of an adventure, and so the two of us took jobs in Chile. And so my job, as you heard Toby say in the introduction, was working at the European Southern Observatory, which had just built 4 of the biggest telescopes on the planet. I mean, why build 1 when you can build 4? So I went there, and my job was to split my time between doing my own research and supporting observations at the telescopes that were very imaginatively called the Very Large Telescope. So whilst I was in Chile, I was still working in this field of quasar absorption lines, thinking about the chemical evolution of galaxies, but I was getting a bit frustrated. I was getting frustrated because I had lots of questions about galaxy evolution, but this field of quasar absorption lines is a game of chance because you have to find these rare, bright, distant quasars, and then you have to cross your fingers that maybe there's a galaxy between it and us. And so it was very, very difficult to do well-posed, well-crafted experiments with large samples. And so I started to think about how I could study galaxies in a different way, where I had more control over the way I could find the galaxies and have some bigger samples. And so I'd been spending my time in Chile thinking about this problem, and I thought I had come up with a way of assembling these kind of large samples, but I was in need of a like a good science question. Like I feel like I had cracked the technical piece. I just wasn't quite sure what I wanted to do with it. Then I moved to Victoria. So I moved here in 2003 to take up my position at the University of Victoria. And it was in my very first year that I was at UVic that I went to a seminar. And this seminar was actually by somebody who I had known for a number of years, just as a friend and a colleague, but I'd never worked with him. And his speciality was studying what happens when 2 galaxies collide with one another. So this so-called phenomenon of galaxy mergers. Now, before I tell you about his seminar and what came afterwards, a question that I often get is, well, wait, galaxies merge, but space is really big, and isn't it expanding? So galaxies are getting further and further apart. Yes, both of these things are true. Space is really big, and it is expanding. And so in general, yes, galaxies are getting further and further apart. But galaxies are social creatures, and they like to live in groups or in clusters. They're like little townships. And so whilst the universe as a whole is expanding, these little townships of galaxies, they feel their local gravity more strongly than the expansion of space. So they're kind of decoupled from this overall expansion. So the Milky Way, for example, the Milky Way is in a group that we call the local group. There are about 50 galaxies in the local group in total. And the local group is not flying apart from one another. We call self-gravitating. And the galaxies in these groups are sort of buzzing around locally. And this is what sometimes causes them to get just a little bit too close to one another, and they capture each other gravitationally. So this merging of galaxies, as I mentioned at the beginning of the talk, is actually how we build up from small things to massive things over time. And it's not as rare as you might think. So in the nearby universe, so in the present day universe, about 2% of galaxies are in an interaction at any given time. So it's not that uncommon. And in the early universe, when things are much more dense, it's even more common. Okay, so I went to this seminar all about galaxy mergers, and my colleague was basically, he was just trying to count them. How common are these galaxy mergers? And at the end of the seminar, I raised my hand and I said, what happens to the chemistry of galaxies when they merge? And he said, I don't think anybody's ever thought about that before. That was the start of the last 15 years of my life. So I started off working on galaxy mergers because I was interested in what it might do to the chemistry. But then it opened a Pandora's box where I've spent the last decade and a half studying many aspects of mergers. And so that's what I'm going to tell you about now. So there has long been a theoretical picture of what should happen when two galaxies have a close gravitational interaction. So they come in, they have this close passage, and then they swing out, and they have a couple of these close, we call them flybys, as they're capturing each other gravitationally, and eventually they coalesce into one massive entity. This can cause some pretty extreme fireworks to happen, because as the galaxies have this first close passage, they start to tear each other apart due to gravitational forces. So when we look in the night sky, we can see pictures of these interacting galaxies, and they just look like train wrecks. So rather than the nice, well-organized spiral galaxies or the nice, smooth, elliptical galaxies, we occasionally see these train wrecks of galaxy mergers that are just all over the place. They're very, very irregular. They have long streams of stars that have been ripped off them. They have shells of resonating material that extend many hundreds of thousands of light years out into space. And all of this disturbance plays havoc with the guts of the galaxy. And in particular, one very important thing happens. And that is that the gas that is in the galaxy, because when we think of galaxies, we think of their starlight, right? When we see pictures of galaxies, we're looking at their stars. But in between all of those stars, there is gas as well. And so all of this havoc and chaos actually causes the gas to mostly flow towards the middle of the galaxy. And so the theory says that you should get this pileup of gas in the middle of the galaxy. And the more gas you have, the more stars you should be able to form. And so theory predicted that we should get big bursts of star formation in the middle of galaxy mergers. The other thing that the theory predicted was that that same inflow of gas into the center that was causing this burst of star formation, if that gas can get all the way down onto the central supermassive black hole, then we can make one of those quasar things, one of those really luminous accreting black holes. So these were the things that we ended up trying to test observationally. The theory was well laid out, but we wanted to test it observationally. So the challenge was we had to find some of these mergers. So as I've alluded to, they are around, but you still have to sort through an awful lot of galaxies to find your prints. And so we were very lucky in the early 2000s. There was a massive new survey of galaxies that had recently been completed and made all of its data products public. And so we used this survey to go out and hunt for these needles in haystacks. And we did it firstly in a very primitive way. Okay, because we were wanting to look for galaxies that were on the cusp of merging together. Okay, so what did we do? Well, we looked for galaxies where there were two things very close together on the sky and that seemed to be at more or less the same distance, because we didn't want just sort of two things at very different distances that were just projected close by. Okay, easy peasy. And then we wanted to be able to measure how many stars they were forming, and we wanted to be able to measure how much material they were accreting onto their black holes. And amazingly, all of that information is captured in just taking one picture, one spectrum of the galaxy. You have all of that information in there. And so we were able to do statistical studies that proved the theoretical predictions were correct, that star formation was greatly enhanced in these mergers, that accretion onto the black hole was also greatly enhanced. But we still only had part of the picture, because we were capturing these mergers when the two galaxies were still separated. We wanted to be able to also trace what was happening in the late stages, because again, one of the important theoretical predictions was that in this late stage, all this activity that had happened early on would eventually exhaust the galaxy, would use up all of the gas, and the galaxy would basically just fade and die. So in order to test this last prediction, we had to find galaxies at this very last stage, when we didn't just have two separate galaxies, but we just had that one train wreck left. This is now a much harder thing to do, because finding the two separate galaxies before they merge, easy peasy, because I just go to my catalogs of positions and say, find me two things that are close by. But I can't do that if I'm just looking for one recently merged galaxy. And this is really where the technology of the 21st century comes in, because this is where artificial intelligence has made a huge difference to us. So what we have done is we have gone to those computer simulations that I talked about at the very beginning of the talk, where we can simulate essentially a universe in a box, where we can generate hundreds of thousands of galaxies and watch them evolve over cosmic time, and where we can find mergers happening in this simulation, and we can identify them very easily. We have algorithms that go into this box and trace what the galaxies are doing. Then we take these simulated galaxies and we try to make them look like realistic galaxies. So what does that mean? Well, when we look up in the night sky with our telescopes, we have the atmosphere in the way, makes things blurry. Okay, so we have to put that in there. There are other things in the night sky around, kind of contamination, so we put that in there as well. So at the end of this process, we basically have these simulated galaxy mergers that we have tried to make look as realistic as we can. Okay, then we train an artificial neural network, which is a fancy artificial intelligence routine, to tell the difference between mergers and normal galaxies. It's just like training things to recognize the difference between cats and dogs or cupcakes and donuts. So this kind of machine vision is really bread and butter these days. And so we've applied it to galaxy classification. So now we have this neural network that we can feed hundreds of thousands, millions of images to. And just like that, it'll tell us which one is a merger and which one isn't. So now we've been able to assemble these very, very large samples of these late-stage mergers. And we've been able to quantify whether or not they have indeed shut down their star formation. And actually, the signal that we find is much, much stronger than any theory had ever predicted. It's very, very rare in a scientist's life that you do an experiment or make a plot and the result is just so outstanding, so far beyond the size of your error bars that you kind of go, whoa. But this is what happened with this experiment. We found that the frequency of these shut down galaxies was about 50 times greater than was expected. There was no ambiguity here whatsoever. It was a very, very clear signal. So this has been a very steep, a very exciting learning curve that in just a century, we have gone from not knowing whether there are other galaxies in the universe to appreciating that we live in a family of billions of galaxies, to being able to understand not only how those galaxies have evolved into the massive entities that we live in and that we see in our local group around us today, but also being able to employ these cutting-edge computational techniques that we combine with our observational technology and our computer simulations to be able to extract and do these kinds of experiments. So thank you very much for your attention. I'm happy to take any questions.
All right, so do we have questions from the audience?
There's a question over here.
All right. Yeah, okay, please.
With this method, I mean, we're in a galaxy, we're interested in ourselves, and we want to know why this galaxy has us. Is there anything in the discoveries you made that clusters the characteristics of life in this universe as a possibility in other universes?
Okay, so I have to repeat the question for the live stream. So the question was whether my research touched at all on the origins of life, both the origins of life on our planet, but also the potential for origins of life elsewhere. So this is not the topic of my research, but it is a very active topic of research. In terms of some of the discoveries in the last 20 years. So we've realized that planets around other stars are extremely common. So we certainly are not unique in terms of our solar system. Astronomers have discovered not just planets around other stars, but planets the same kind of mass as the Earth in the so-called habitable zone. So that means the distance from a given star at which liquid water can exist on the surface. So there are these steps towards the realization that our Earth is not really unique. Potentially the most exciting thing, I think, is now the experiments we can do to start to look for biomarkers in the atmospheres of these planets. So the technique that I described in my talk, in which I'm looking for galaxies in front of bright background quasars to study them, you can do exactly the same with planets as they pass in front of their host star, that you can figure out the composition of their atmospheres based on the star spectrum. And there are certain, we call them biomarkers, that we don't expect to be there unless there is life on this planet. So the short summary is that whilst my research doesn't touch on this, there is a lot of exciting work in that direction.
It's basically chemistry on a smaller scale. What? There's a question here.
Is there only one sun in the universe?
So the question was, is there only one sun in the universe? So I think that depends on your definition.
More than one universe, then I guess.
Okay, so the question was there, is there more than one sun in the universe? And is there more than one universe? So in terms of, is there more than one sun? Well, the sun is a very, very average star. I hate to break it to you. We're really, really not special. So the sun is an average size star. It's a kind of average age star. So stars like our sun are 10 a penny in our Milky Way and in other Milky Ways. So in that sense, the sun is not unique. It's also not unique, as I said before, in terms of hosting planets. Is the universe unique? You know, theorists have a field day in terms of being able to write down mathematically that there is no reason why other universes can't exist. But how we prove it experimentally, that's the tricky part.
There was a question here.
So the question was, how will the James Webb Space Telescope impact my research? So for those of you who might not be aware, so the James Webb Space Telescope, or JWST, so this is in some ways the successor to the Hubble Space Telescope. Not exactly, it works at slightly different wavelengths, but it is a space telescope, and it's much bigger than Hubble. And so it's going to completely revolutionize many aspects of astronomy. For my particular research, so one of the things that Webb is good at is working at longer, redder wavelengths. And so it's really good for looking at more distant objects. And so all of the merger work that I've described, we've done in the nearby universe, where it's easy because things are bright and we have large surveys for them. But whether these same mechanisms operate in the same way in the early universe is still completely unknown. And so Webb will allow us to look at that.
As the stars or galaxies merge and come together to the end of the stage, you said star formation shuts down. Is that because the hydrogen is being all consumed, or what's going on that they're shutting down?
Okay, so the question was, what about the merger causes the star formation to shut down? I wish I knew the answer. So this is actually exactly what we're trying to figure out right now. So the theory predicts that all of these fireworks caused by the burst of star formation and the quasar in the center produces so much energy that it just pushes all of the gas out. That's what the theory says. But when we look at these merged galaxies, even the ones that have shut down their star formation, they still have gas in. And yet somehow they're not forming stars, even though the fuel for making the stars is still there. So that's going to be the next stage, is figuring out. We don't know. We don't know. So for some reason, they've shut down their star formation, even though they've still got gas. There are a few different ways that one could explain this. And so actually the next step is to use a different type of telescope. It's to use a type of telescope that can study this gas in emission directly, to map where it is and what it's doing and why it doesn't want to form stars anymore.
All right, so I try to keep track here. We got 5 more at least. I think it was here in the back first.
You mentioned that most galaxies have black holes at the center. When these galaxies
Right, so the question was, each individual galaxy has its own supermassive black hole. So what happens to those black holes when the galaxies merge? It's a great question. So just as the galaxies are merging, those two supermassive black holes are also predicted to merge. And people have tried very, very hard to kind of catch this in the act. This is where a different field of astronomy comes in. So this is the field of gravitational wave astronomy. And so there's been quite a bit about this in the news over the last few years. So there are these incredible experiments that are able to detect the disturbance in space-time as black holes merge. And this has been detected. But there are actually two different flavors of black holes. One flavor is the supermassive type that lives in the center of each galaxy. The other type, we call them stellar mass black holes. That's where just one individual star ends its life and leaves its remnant, and its mass is more or less the mass of the sun or so. So when astronomers have detected this gravitational wave signature from merging black holes, it's when two of these so-called stellar mass black holes merge within our own galaxy. Trying to detect the merging of two supermassive black holes, it sounds like it should be easier, right? You got two massive things colliding with each other. It's actually harder for our current experiments because the wavelength of the signal, we need different experiments to capture different wavelengths. So it's a little bit like whether you can hear high tones or low tones. And so there are certain tones that the human ear is deaf to. And so our current gravitational wave experiments can hear stellar mass black holes merging, but they don't hear the right tone for these supermassive ones. But those experiments are coming, but they need to be in space because they need to be able to measure these really, really long baselines. So that is the direct detection of that happening is coming.
I'm just curious, you said in the very early part, in the history part, we were looking out into the galaxy, we were seeing fuzzy smudges on things, but we basically didn't think there was such a thing as other galaxies. And I'm just curious, what was our cosmological model at the time? Like, had we just not accepted infinity yet, or like, were you scared by what we looked at?
Right, so the question was, what was our sort of cosmic view at the beginning of the 20th century, and why was it so difficult to accept that there were things so distant? I think it was really, it was maybe a lack of imagination at the time, but the idea of the distances that you would need to be at to be beyond the Milky Way. So people were measuring, so at that time, people were measuring the diameter of the Milky Way. And they were doing that using very similar techniques, these kinds of variable stars. And already those numbers seemed so mind-bogglingly huge that to then imagine that there could be things the same size and yet so far away that they're so tiny on the sky, I think it was just so difficult to sort of wrap our minds around that. And I think that there are many examples of this in history, things that seemed like science fiction that we now take for granted. But at the time, it was just this kind of mental phase transition that needed to happen.
I lost a little bit of track whose turn is, but I would rather say I prioritize the center for now. So there was one question here in the center. Yeah, somebody here had a question. If not, a couple of... There you go. Okay, please.
What do you have figured out as far as the formation of galaxies?
So the question was, what do we have figured out in terms of the formation of galaxies? I could probably talk for a whole other, well, I was going to say hour. I mean, we give entire graduate courses on galaxy evolution. Maybe just the highlights are that in the early universe, after the Big Bang, the distribution of matter is not smooth. It's slightly clumpy. And that clumpiness forms the blueprint for where galaxies are going to form. They're the slightly dense parts of space where gravity is going to start to bite and bring things together. And that inhomogeneity in space is there in the dark matter as well as in the atoms. And so these are the wells where things form. In terms of the kind of patterns that we see in galaxies, so we see these spiral arms, we know that galaxies are rotating. That actually happens because, again, of these mergers of galaxies whipping past one another. They spin each other up. In terms of the black holes, that's actually one of the really big open questions, where these supermassive central black holes come from. I've talked about them fairly glibly, but we have no idea how they get there. The stellar mass black holes, we kind of understand the process of stellar evolution that makes these low mass black holes, but things that are millions or even billions of times the mass of the sun, we don't know how those have got there. So there are some things that we think we have a pretty good handle on, but then there are other things that we still have no idea, which is good news for me, because otherwise I'd be out of a job.
I was wondering, is it possible for our galaxy to merge with another galaxy?
Yes. And it's going to happen.
When?
Okay, so one of our near neighbors, the Andromeda Galaxy, which is in Messier's original catalog, it's M31. Andromeda is a very similar galaxy to ours. It's a large spiral galaxy. It has a supermassive black hole at the center. It's in our local group, and it is moving towards us at the frightening speed of 200 kilometers a second. Okay, so luckily it's a long way away, so you don't have to worry about your weekend plans or anything. But eventually, we will merge with the Andromeda Galaxy. Now, one of the important things to know is that most of the real estate in galaxies is empty. So the distances between the stars is very large. So even when galaxies merge, individual stars don't crash together. Now, by the time we're merging with the Andromeda Galaxy, we're going to have other problems, because the sun is going to have expanded into a red giant and scorched the Earth. So we're not going to be around to worry about this anyway. But even so, the sun is not going to be in any danger, or is very unlikely to be in any danger of collision with other stars. It might get catapulted out to sort of larger distance from the center of the galaxy. But that might not be a bad thing, because if you've got two supermassive black holes merging, and I mean, I don't think I'd want to have a ringside seat for that anyway.
Okay. Close one. Please.
The collision of galaxies involves enormous amounts of energy conversion. And I'm wondering if there's some possibility that dark matter is, for the want of a better word, excited or made to act in such a way that it might become, or its characteristics become detectable in some way. Is there something special about the merger of galaxies and the potential detection of dark matter in a more tangible form?
So the question was, does the merging of galaxies help us detect dark matter? Okay. Actually, this has been done, but not for the merging of individual galaxies, but on a larger scale, the merging of clusters of galaxies. So just as galaxies are moving around and they sometimes have encounters, the same is very rarely, but it does happen, for these cities of galaxies to interact. And a number of years ago, there was an observation of a cluster called the Bullet Cluster, and it was actually two clusters that were colliding. And what happens is the gas that's in these clusters, so in between the galaxies, there is hot gas. The gas in these clusters, it feels a shock. As you're trying to bring two hot blobs of gas together, there's a shock that happens. Dark matter by definition, doesn't interact with anything. And that's why it's so tricky to pin down. So you have this collision where the gas shocks, but the dark matter just keeps moving straight through. And so astronomers were able to kind of make this picture of where the hot gas was versus where the dark matter was, which we really just trace through a technique called gravitational lensing. And so they were able to see exactly what you propose.
That's a question here.
So the world has spent so much money over so much time to get the stage to which, how close we are to the Big Bang. So the first question is, how close are we to it? And in your foreseeable future, how close do you think we will get? And postulate if we actually get to the event, will there be a white flash?
Okay, so the question was a big question. How close are we to the Big Bang? And how close might we get to the Big Bang? So I'm going to interpret this question as how far back in time we can see. So how close to the Big Bang are we able to observe? So this is a very pertinent question, in particular in the context of the earlier question about the James Webb Space Telescope, because before the Webb telescope came online, so when I was doing my grad studies, for example, the earliest galaxies that we could find were about 2 billion years after the Big Bang, which felt pretty primordial at the time. Now with James Webb, and Webb has only been online for a couple of years, and yet already we're able to find with Webb galaxies that are 400 million years after the Big Bang, which is in astronomical terms is the blink of an eye. So we're gonna get really, really close to the Big Bang, but there is an observational limit beyond which we can't see. So when the Big Bang happened, it creates matter in this big fireball. And the photons can't move freely through this fireball. It's like this hot plasma that we can't see through. And so as the universe expanded and cooled and atoms formed, that's the moment at which it becomes transparent and we can actually start to see through it. So there is actually this sort of fundamental limit beyond which we're not going to be able to see galaxies. Now that's the galaxy context. The other way to answer this is that in some way we've already seen as far back as we can see, because that echo of the Big Bang happening, so that hot fireball, that has already left an imprint in the night sky that we've known about for decades. In fact, this was observed back in the 1970s. The astronomers who first observed it didn't know what they were looking at. They could just detect this relic radiation. But eventually, astronomers figured out that this was the relic radiation left over from the Big Bang. So in terms of how far back we can look to study galaxies, we're already really pushing the limit. But in terms of are we actually able to see the Big Bang? Here is a fun fact. Old-fashioned televisions, when you used to be able to tune the dial to the channel. All right. So if you tune the dial in between channels and you just get static on the TV, about 1% of the static that you see on your TV is radiation coming from the Big Bang. So you should never complain that there's nothing to watch on TV, because you can just sit and watch the Big Bang on TV. Do galaxies always rotate in the same way? So that's a very interesting question. There have been studies that have tried to look at the handedness, essentially, of galaxies, and claim that there is an excess in one direction. It's a bit puzzling because it shouldn't be that way. But maybe I just leave the answer as maybe.
Good option for our next PhD project. Alrighty, we have more questions. Ah, all right.
You mentioned AI supporting your research. It's obviously moving into a whole bunch of fields. How do you see it progressing for the next generation of astronomers and finishing your work?
Yes, so the question was, how do I see the artificial intelligence evolving in terms of the way that we use it in our research? So I think it's fair to say that, 5 years ago, AI was a real novelty in terms of scientific research, not just in terms of astronomy, but I think in any science, it was a rarity to see it involved. Now I see it everywhere. And there is barely a graduate student in our department who can't run these algorithms. So I think it's really now bread and butter. But powerful as it is, I think that there are pitfalls associated with using it. And I don't mean sort of from the conspiracy theory aspect of it. I mean, just because we have a powerful tool doesn't mean we're necessarily learning something new. And so I think it's true in many sciences that we are drowning in data. There is so much data available now. And so having these powerful tools feels as if we're making progress. But I think where we have to be very cognizant is that we're still able to ask good questions. Because just because you can do all this fancy stuff with the data doesn't mean you're necessarily learning something. And I think that is where the scientific skill is not going to be replaced, because we still have to be able to look at the research landscape and think in the context and think about the relevant questions to ask so that we can get these algorithms to work for us. They can't think up the questions for us, at least not yet.
Do we have any idea how long the universe will continue to expand? And also, will people ever be able to travel? Not we, but people with man will ever be able to travel to other galaxies?
Okay, so the question was, do we know how long the universe will continue to expand for, and what are the prospects for long-distance space travel? Okay, so the fate of the universe, sort of post-Big Bang, depends on essentially the acceleration of the expansion. And so if I had been answering this question 30 years ago, I would have said, all we need to do is measure how much mass there is in the universe. Simple little thing. And then I can compare that to some kind of critical value. And if my value of the actual mass is bigger than this critical value, it means that eventually the expansion is going to slow down, turn around, and the universe will recollapse. And if we don't have enough mass to do that, we'll just keep expanding forever. The spanner in the work, or the fly in the ointment, has been this other stuff we don't understand. So we have dark matter, but we also have this other stuff called dark energy, which, if it's possible, is even more mysterious than dark matter. And this dark energy, which we have detected the presence of it, we see that it has an effect, but we don't know what it is. It works in an opposite sense to gravity. So whereas gravity likes to sort of pull things together and slow down the expansion, dark energy is like a pushing force. And there is a lot more dark energy around than there is mass. And so, in the last few decades, we've come to appreciate that the universe's expansion is actually just getting faster and faster and faster. So in the very, very distant future, the universe will be so immense that when we look out into the night sky, we won't be able to study other galaxies because they'll just be too far away. We'll see the stars in our own Milky Way. The Milky Way won't be ripped apart. But the study of galaxy evolution will be infinitely more difficult. In terms of long-distance space travel, at the moment, that's still very much in the realms of science fiction. We still don't even have the capacity to travel to other nearby stars, let alone other galaxies. But, going back to the earlier question of, why didn't we realize that there were other galaxies out there? Ultimately, we're kind of limited by what we know at any given time. And so I never say never.
All right, last call. All right, just speak up. This is your last chance. There is somebody there. Yep.
My question is concerning the AI models that have been used to predict mergers. Is it possible to use the same existing model to ask other questions, maybe possible exceptions, or anomalies, maybe 3 galaxies merging, or when they do merge, something else happens?
Yeah, so the question is, can we use the same kind of AI models to extend the research into a sort of a different regime? So one of the limitations with not all, but most AI is that it works in a way that we call supervised, which means we tell it what to look for, it learns from us, and then it kind of goes off and does its job. So that is the way that we've used it as I've described so far. But there are ways to kind of let it run more freely in a more exploratory way. And this is, I think, the domain that you're referring to, where you don't give it your own preconceptions and you sort of say, go out and tell me what you see. So yes, it certainly can be used in that way as well.
Happy to take one more question?
Sure.
All right. I have one over here.
Well, I think you did such a great job tonight. You did a fantastic job. Can you come back and tell us about snorkeling?
Be careful what you wish for. Be careful what you wish for. Yeah, you wouldn't get me off the stage once I start talking about nudibranchs.
All right, so I guess it's time to close up, but I think I take the privilege as the host to ask the last question. So I was very intrigued when you said, okay, what a person would tell in the 20s and then 70 years later. So may I ask you to look in your crystal ball, and what would a person tell, like my kids, they are right now tiny, so what would they tell their grandparents in 70 years?
I think we will have detected life elsewhere on that timescale.
Wow. Okay, that's an excellent end.
Not necessarily,
Perfect, yeah.
intelligent life, but some kind of at least biomarker, microbial life.
Okay.
Yeah.
Fair enough.
You heard it first here.
Right, okay. Great, yeah. Well, I mean, I asked last time I asked a question what people think is more likely to find a room temperature superconductor or life outside of Earth, and life outside of Earth won. So I guess people trust the astronomers more than the condensed matter physicists. Thank you very much, everyone. Yeah, great. Right, again, thank you very much. Oh, that was fantastic. All right, so we are back in, I think on the 13th in February, and then we are going from the largest scales, which we had today, then right down to the quantum regime, to the smallest objects. And I hope to see everyone back then. All right, thank you very much.